Hello, and welcome to Self-Learning AI in Automotive Software, a webinar showcasing how self-learning AI has helped CARIAD build an automotive software powerhouse. My name is Stephen Wicks. I am the editor at Automotive IQ, a division of IQ PC, and I'm joined today by Andreas Weichslgartner, who is a senior technical security engineer at CARIAD. This webinar is sponsored by Code Intelligence. CARIAD has been building one unified software platform for all Volkswagen brands to provide them with reliable software and digital best practices. In recent years, the industry faced extensive industry regulations and an array of dangerous and costly vulnerabilities. By introducing feedback-based fuzzing, an advanced white box testing method that uses self-learning AI to uncover deeply hidden bugs and security vulnerabilities, CARIAD was able to find and fix potentially dangerous issues early in the development process. In this talk, Andreas will explain how CI Sense, Code Intelligence's test platform for CI/CD integrated software testing, enabled CARIAD engineers to accurately weed out severe issues early in the development process, while enabling them to comply with industry regulations such as ISO 21434. CI Sense has already helped CARIAD find over 30 issues, including critical security vulnerabilities. By joining today, you too will understand how you can use self-learning AI to uncover deeply hidden bugs and security vulnerabilities. After Andreas's presentation, we will be hosting a Q&A session with the audience. So if you do have any questions, please use the question box on the bottom left of the screen, and we can read those out to Andreas at the end, and he will answer your queries. Please note that this session will be available on demand, so after this, look out for the link that will be emailed to you for you to watch it back. So without further ado, I'll hand you over to Andreas and we can begin.
Thanks for the introduction. So now I want to talk about fuzzing and how we use it in CARIAD. So just in the beginning, a little overview what is CARIAD. So we do the software and hardware for the 9 brands in the Volkswagen group, so Porsche, Audi, Volkswagen, and so on. Like there should be 14 million connected cars, and the goal is that we have one consolidated software platform, which serves then for all the different brands, and we have a central software stack maintained by CARIAD. And yeah, so basically we have like 2 different stacks. Like one is like safety related, which deals with all the driver assistance and so on, and the other one is the infotainment, the user experience, and yeah, so there we have different requirements, different software stacks, and also different cooperation partners. So on the driver, on the advanced driver assistance side, we have a cooperation with Bosch, and also on the hardware system on chip, there we use like Qualcomm, and in China we have a cooperation with Horizon Robotics. And on the other side, on the infotainment digital experience side, you can see that we use Android systems for the infotainment system. So yeah, it's quite different software we use there and different requirements. And this also then deals later with the testing and challenges we have to face. But in recent use, you might have heard there was like one CVE dealing with the glibc. So glibc is the standard C library in Linux systems. And there was a privilege escalations called Looney Tunables. And basically this vulnerability helps, or attacker can exploit to get privilege escalation on your system. It's currently also some reports that it's actively exploited by some actors. And in their email, in the security mailing list, they described that they didn't discover this issue by fuzzing, although like they wrote a fuzzer and it discovered it within a second. So like AFL++ and libfuzzer, there's the 2 mainly wide used fuzzer, discovered this issue very fast. And the other well-known security issue was like in curl or libcurl. So this is a widely used library command line tool to get data between different places and also download data from the internet. So probably everyone has these dependencies, and the maintainer wrote that this is the worst curl security flaw in a long time. So in the end, it turned out it was also a heap overflow in curl. And like there's a nice blog post by the maintainer where he mentioned that, yeah, 41% of the security issues they had in curl are related to a memory safe language. Yet they use all available static code analyzers they can find, but none of them has spotted this issue and this specific vulnerability in curl. So also there it's some parsing issue with very long DNS names, and then you end up in a heap buffer overflow. So what I want to talk about today is first I want to analyze where does this stem from, and like are there some patterns we can find in the vulnerabilities we have in the automotive industries. And then in the later part I want to discuss like how we can use fuzzing to detect these issues early in development process and save money and time to prevent these vulnerabilities. So what are the main root causes for vulnerabilities in the automotive space? First, some terminology. So I will use some acronyms further on, and just to get this clear. So the CVE is a common vulnerability and exposure. It's a unique ID assigned by certain authorities, and you can use this ID to look it up, and it identifies a vulnerability uniquely with this ID. Then the CVSS is the severity score. This is also industry standard in different versions. You can calculate the impact and the severity of a vulnerability. You have different fields like the attack vector, what is the privileges that are required by an attacker, and so on. And with this, then you can have a calculation of how severe it is. You can have a base score, which is provided by the NVD. So this is the last one. This is the National Vulnerability Database, where all the CVEs are stored, and each CVE then gets a CVSS base score applied by NIST, and you as a downstream consumer of these vulnerabilities then also can calculate based on your system an adapted score on the base score. So if your environment is different, you would need further privileges, for example, to execute something, then you can use this in the recalculative CVSS score, and severity could rise or decrease based on your system. So this is the main acronyms we will use further. And so for example, the common weakness enumeration is also another acronym. This is basically a bug class. So we have different IDs for different weaknesses. So one weakness, for example, the CWE 787 is out of bounds right, and we see here also the MITRE, one US organization, also they have a list of the most dangerous software weaknesses, and number one is this out of bounds right. Then we have out of bounds read, and here also we have a score how critical they score these weakness classes. So we see like the higher the score, the more critical this weakness is. And in the last column, we see if it's a memory safety issue or not. And these are some selected classes for known automotive vulnerabilities from the past. And we see there are a lot of memory safety issues, and also input validation is another issue, and improper neutralization of special elements, so OS command injections. These are also things we can detect with fuzzing, which we will also detail later. So how we can detect issues here. So now we want to have some overview, like what are the issues we can find in automotive software. So there's one paper from 2019. What they did, they queried the NVD database with certain search terms. So they have some categories like chipset. So these are like from two prominent vendors in the chip space which provide chipsets for the automotive industry like Exynos and Snapdragon. Then we have the various OEMs, and then there are some automotive specific technology like OBD2 and a diagnosis port, for example, or like steering control and so on. And you query the database, then afterwards you filter out the false positives, and then you have a list of CVE which are related to automotive vulnerabilities. I used this methodology and used current data from 2023, and also had to filter out a lot of false positives. For example, SEAT is a car brand, but also SEAT is the same word, and it's not related to SEAT, so there's a lot of manual work to have been done. You could also use like some different classifiers like CPE, which are also used, like this is the common platform enumeration, which helps a bit, but yeah, nevertheless, here are the results. So we can see the biggest portion is like Bluetooth. There is a lot of CVEs reported to Bluetooth. Then we have a lot of CVEs reported to Snapdragon and Exynos, so the chipsets, and only very little CVEs are reported by OEMs themselves. So this may also be that like OEMs are not so active in getting CVEs assigned, while in other industries, for example, Bluetooth, there's a lot of Bluetooth vulnerabilities in Android, and Google, they just submit a CVE for each of their vulnerabilities, and then it's easy for you to track it. Also, the Linux kernel themselves, they say they don't believe in the CVE system, so for them a bug is a bug. So they say you shouldn't rely on Linux CVEs, and you should just update the kernel to the latest version. So this is their approach, but in other areas, CVE is still the industry standard. And just going to the Bluetooth here, so we see this is the list I stared at for some time to filter out all the false positives. And this reoccurring pattern there was like, oh, in Bluetooth, there is a possible out of bounds read. So you see the bounce check you have to do in parsing Bluetooth package is very hard. You have a lot of bounce checks there, and it seems it's very hard to get these bounce checks right. And it seems in 2019 someone wrote a lot of tests to check if these bounce checks are right, and there were a lot of findings in the Bluetooth stack of Android. And if we plot this over time, we can see that until 2014, it wasn't an issue because it seems no one tested stuff. And then after 2014, we see a steady rise, especially like in the red and yellow ones. These are the memory safety related issues, like out of bounds read, out of bounds write, buffer overflow, and so on. And yeah, in 2019, we see also this peak here. I think it relates to this lot of Bluetooth vulnerabilities. And here we plot the same weakness classes, but in the overall manner, and now sorted by CWE classes. And we see the most frequently occurring CWEs, the buffer overflow. Then we have out of bounds writes. Then we have improper input validation, and so on. And yeah, so the most prominent or most frequent weakness classes deal mostly with memory safety plus like improper input validation. So if we could test these categories in a proper way, then we would already have weeded out the biggest part of the vulnerabilities we have in this kind of data set. And if we just would classify the things through memory safety and non-memory safety, so we should just define what is memory safety. So memory safety is that all memory access adheres to the semantics of defined by the language. So this means you access an object only within its bounds and with its lifetimes. And in C and C++, we have unchecked pointer arithmetic. So if you have a pointer to an object, you can access it out of bounds and out of lifetime. So you have no memory safety guarantees by the language. Also note here, like memory safety is different to functional safety. So memory safety is a concept in languages, and functional safety is from functional safety as defined in ISO 26262. And so just keep this in mind. And the spatial memory deals with the access of the object within its bounds. So it means you do bounds checking, that you don't access anything out of bounds. There are proper ways in C++, for example, that you can access a vector or an array in a bounds checked manner during runtime. But the standard way you would access it, it isn't bounds checked because it has some runtime overhead. So if you want high performance, then people often omit the check, and then if it fails, then you have a problem. And the temporal memory safety means that you only access an object which is still valid. The basic class here is like use after free, when you can access still an object while already you freed the memory. This is harder to check. In Rust, you have the borrow checker for this, and to implement this in C++ would be very complicated. So overall, in this test set we got from NVD based on the search terms, we see that roughly half of the vulnerabilities stem from memory safety issues. If we also take a look at the severity, so a vulnerability can have different severities based on the CVSS score. So a CVSS score from 10 is the highest one and 0 is the lowest one. So I think above 7 it's high and above 9 it's critical. And we see here that the buffer overflow, like in this violin plot, it estimates the distribution, and here the distribution is very towards the 10. So all buffer overflows have normally a very high severity, while, for example, what we see on the right side, the integer overflow, it's much more flat, or like the improper authentication, it's more distributed. There are very different vulnerabilities, while the memory safety issues, they always seems to have a higher severity than other weakness classes. So these vulnerabilities are very dangerous. This finding is also backed up by data from Project Zero. So they collect actually exploited vulnerabilities in the wild. So they have a spreadsheet you can look up where they track all exploited vulnerabilities, and they also categorize them not by the CWE system, but more broad system. So they have like one category called memory corruption. And so this is the memory safety issues. And you see here like memory corruption and information leak and use after free. It's like 75% of all the vulnerabilities which are exploited stem from this kind of weakness in your program. So attackers like to exploit memory safety issues. So I hope now you agree with me that we have a problem with memory safety bugs in automotive software, and we should like either switch to a memory safe language, so we rewrite everything in Rust. Of course, this is not practical. We have a huge legacy stack and a huge ecosystem also, for example, in the AutoSAR stack, which is still on C++, and also some microcontrollers are still in C. But of course, if we are able to and can have a new project in Rust, then it's nice to have this in Rust, because then we have eliminated like already this big pile of issues we could have. But if not, we need to test and identify these vulnerabilities early in the process. So what we also see here, this is like the normal software development process we use in the automotive industry. Also, if you take a look at the ASPICE process, like what you have to do at which stage, they also have some similar V model. Of course, in the agile software development process, you go through this V several times for each product increment, and you could do something at each step. So I will focus more on the first part of the V model. And now we take a look like how we can prevent and detect the bugs early on. So normally in the beginning, you always do a risk assessment. So here you see like how this process looks like. We have certain assets we want to protect by certain security properties, and we have goals for them. For example, one asset that we want to keep it confidential, that no attacker can read its contents, or we want to ensure that's integrity. And on the other side, like we have threats and which tackle our security goals. So one thing here would be that if we have something that we want, an asset we want to protect, and we do this in a memory unsafe way, then a threat actor could like exploit this memory unsafety, and it could increase the attack feasibility, and we can have a high risk. So here we also need to treat the memory safety issue as a threat to our assets. Like in an easier way, I like this one is much more understandable for a developer. So you have this rule of two. This is from the Chrome documents. So where they say like you have like 3 different things, you can process untrustworthy input, you can have a memory unsafe language, and you can execute it without sandbox. And if you do all 3 of these things, you're basically in the area of doom. So you shouldn't do this. You should at least have like one, mitigation, or one thing should not be there. And so if you have an untrusted input parsing with a memory unsafe language and you don't have a sandbox, you have a problem. So you could introduce a sandbox, or you don't use a memory unsafe language, and so on. So I want to focus now. There's a lot of things about sandboxes and so on, a lot of new development in like WASM or micro sandboxes, micro VMs you could use, but this is not part of this talk. So here I want to talk about how we can test the process of untrustworthy input, or how we can test memory unsafe constructs. So fuzzing seems to be the best tool to detect these kind of issues, to detect memory safety issues, and to detect when our input parsing of untrusted input goes wrong, or if our checks are sufficient for the input parsing. So it's in a lot of other industries. So the syscaller, the Linux kernel fuzzer, found thousands of bugs in the Linux kernel by fuzzing the Linux kernel. Like the OSS fuzz found thousands of bugs in various open source projects, also in Chrome and so on. There's a lot of findings through bugs, and it's the best testing methodology to find this kind of issues. So how does fuzzing work? The most used fuzzer, a coverage guided fuzzer. So where we have a program, then we could start with some seed things in the corpus down here. So this is an input we want to start. We could also leave this empty, then it will just start by 0. Then the fuzzer uses this input, mutates or something in this input, then it executes it, records the coverage, and see if the program crashes or it hangs. And the fuzzer, it's like some evolutionary algorithm, like tries to maximize the coverage. So by giving the mutation which has like gained more coverage, have a higher fitness, and in the end you will store also new inputs which gain you new coverage in your corpus. And if you then have a big corpus, you can again mutate inputs from your corpus again and again, and try to increase your coverage over time. And you can also, if you store your corpus, you can, by just executing parts of your corpus already, then have a huge coverage of your program. And this, after the last years, it's proven that this kind of fuzzing, like it's very successful in this space. But you need to detect crashes, and out of the box, a lot of crashes you wouldn't detect. So there you have sanitizers. One of the most prominent sanitizer is address sanitizer. This specifically helps you to find memory safety bugs. What it does, it instruments your code, so it adds or like it replaces memory allocation and memory freeing. So in C, it's like malloc and free, and you then have, before the beginning of the object you want to allocate, you add a red zone, and afterwards you add a red zone, and every time you access this kind of zone, you know that you did a violation, and after you freed the object, you will mark the whole area not accessible. So every time you access this object after it's freed, you also get an finding there, and then you get the stack trace. This is implemented in all major C++ and C compilers, and while other sanitizers are not implemented in all C++ compilers, so also that's a problem that we have in C++, very different implementations. There are a lot of compilers. Each compiler can be different, and but the main compiler for fuzzing we use is like Clang. So if it compiles with Clang, you can have all the nice sanitizers and all the libfuzzer. For other languages like Java, there also exists custom sanitizers there where you can then detect, for example, an failed input validation and so on. So this is very useful for memory safe languages where we can use custom sanitizers to detect crashes and vulnerabilities there. But yeah, they're also like from Code Intelligence, they provide certain sanitizers there for Java. I don't give many examples here in this talk about Java because I'm also coming more from the C++ area. But if you do Java, then you can definitely use these kind of sanitizers and detect problems in your memory safe language. So, but everything comes with a cost. So you have the instrumentation during compilation time, and then you have the cost during runtime. So each access to memory has to be checked. You have like more memory because you need to store these extra bytes before and after your memory you allocate. So it's a slowdown of 2x. There is something in specific ARM architectures where you can use like some hardware features and where you could deploy this actually in production code, but normally you don't deploy this in production code, but just using during testing and especially during fuzzing. So how do we get the best out of fuzzing? So I want to give some example here. So this is an automotive protocol stack. And we see here the ISO-OSI network layer model with the 7 different layers. We have different layer 1 protocols. Then on the layer 2, we can have like MAC with VLANs. We can have credit-based shaping for real-time communication. And above there, like we have the standard stuff, TCP/IP, but also different other audio protocols and so on. And on the upper layers, we have like DOAP. This is for diagnostic. We have SUMIP, which is for service-oriented communication inside the car and so on. So you can see here it's a very complex stack. And yeah, in the past, I also wrote some network parsers, and this is very hard to parse this kind of complex protocols because, as I said, they are complex, they are stacked. You can have like be encapsulated in very deep levels. So you can have a VLAN in a VLAN in a VLAN, and the protocol itself normally just starts down, and then you have like one information for the current layer, and then you have an identifier what the upper layer has a protocol in. But you can have the same protocol again and again, so you can have very deep recursions, and you do a lot of mem copy out of these packages then to your local structs. And yeah, often it's a length field, and then this length field you use to copy data, but can you trust this length field? Because the attacker can set this to an arbitrary value. So in the heartbleed vulnerability, this was also an issue because they didn't check the field in the heartbeat mechanism. That just used this length field as it is, and then they had an out of bounds read because of this. So it's very hard. You need a lot of conditions, a lot of if statements, a lot of bounds checks, and yeah, this is very hard to get this right. So what you normally do is like you use test-driven design, you use unit tests, and there are some mnemonics to say, okay, I tested with 0 input, I tested with 1 input, I tested with many inputs, I checked the boundaries, and so on. And you see already there are a lot of test cases you would have to write to get all these behaviors of your unit under test right. And then you only tested, for example, one package scenario. And normally you test like, okay, for this is what I expect. And often you don't know what you don't expect. So for this unknown input by an attacker, and we are here on, we parse untrusted input. So then if an attacker can send us a package, for example, in the Wi-Fi stack or in the Bluetooth stack or over a diagnostic interface, we basically have no guarantee that the fields inside the package are valid, and we would need to write a lot of packages. And this is the combinatorial number of possibilities of packages we could parse simply explode, and it's not feasible to write manual unit tests here. And also, as we heard before from the maintainer of the curl project, like static code analysis also doesn't help here. This kind of memory safety issues, they're highly dynamic. Also parsing the input space is very huge. It's very hard for static code analysis tools to get all of the combinations there right. So what is the solution? You write a fuzz test. And for this thing before, like a packet parser, a fuzz test would look like this. So it's very simple. Here in CI-fuzz also looks similar in libfuzzer. So we had this before in libfuzzer, then we transferred it to CI-fuzz. So it's just different macros. But we have a random data string with a size. We put this to this fuzz data provider, and then we say, okay, give us any valid link layer type. So this is the lowest layer of our protocol stack. So the parser needs to know where it starts. And everything else, we can just give him the random bytes, the remaining bytes in this fuzzer. And then we can say, okay, now you have this kind of package. Now parse it, and then we can let this run. And with the help of the coverage guided feedback, the fuzzer now can explore different paths of our parser, and we can check a lot of conditions we have in our parser, and we can, for example, I detected some infinite loop there, or some stack overflow where you pass over and over the same packet, the same protocol again, and you could then limit the number of recursions or how deeply you can nest your package. And here, like, fuzzing is very helpful, and you will find a lot of issues you wouldn't find otherwise. So there was also some recent publication, like what are the challenges in fuzzing, or what you should take a look when you write fuzz testing. So the idea is that the developers should write their fuzz test case themselves, because they know how the build systems of their project is. They know their code, so they know their interfaces, so they know where the untrusted input goes in. And so it should be very easy for them to write their fuzz test case. And the tooling should also make it very easy for them to just like create a fuzz test case, and then to help them to fill in the different fields there, to transform basically what the fuzzer output into your interface, what you are feeding to your program. So the fuzz test case before, it was very simple because it doesn't use any state, but yeah, it has already, you will find a lot of stuff with it. Of course, there are some other projects where you have stateful application, and there you need to do more things, but also their tooling could help to set up some stateful fuzzing. But of course, on the other side, maybe you should also think about how you write software. If you have a lot of stateful things, if this is really the way, if it's then testable, because even in unit tests, you need to mock all the states. So the fuzzing sometimes uncovers that your project is not really written in the good testable way. But it's not the fault of the fuzzing, but maybe of the overall project. Yeah. But and the last thing here is, like, one person in this survey from this article wrote, like, setting up a fuzzing infrastructure from the scratch must be a daunting task. So we also think this. So we don't want to set up our own fuzzing infrastructure. We want to have something which is there to use, which it's easy for the developer to use, which scales, and where we can utilize specific hardware and resources in a cluster to fuzz at any time, and not be relying on the user who has to set the setup for his own and to maintain it for its own. So these are the requirements, or the things we need from a fuzzing infrastructure. So it should be easy in the tooling side, and the infrastructure should be also there already, and we can just easily integrate it into our own build system. And so how does it look like? We have, of course, some CI/CD system where you can check in your code. You also check in then your fuzz test. As we saw before, it's similar to a unit test. So the developer would write a specific fuzz test case. He could run this locally, but he could also upload this fuzz test case to CI Sense. So this is the server we have. And there you can also, the first thing, you can remotely fuzz and let it run for some time. So don't need to utilize your own hardware. So sometimes you develop in a virtual machine, you have very limited resources, and some projects really take a lot of time to compile. They are in some Docker container, and then you don't have the time or the resources, or if you run this on your local machine, you can't do anything else. So maybe in the past it was a nice excuse to get a coffee and like wait for 2 hours while your program is fuzzing. But of course, we can do this now on the server. We can just load off the fuzz test to the server and then do something else in the meantime. And then after the initial test that we saw, okay, this test compiles, this test maybe has found something, then I can fix it directly. Then we can check in the fuzz test case, and then the CI/CD can run this fast test case itself. It can run it periodically, so we can do some nightly jobs. We can fuzz on a specific date, on a specific time. We can try to all our fast test case. We have already the corpus there on the server in the infrastructure, so we don't have to care about how we store our corpus. We execute all the fast test case, and then if we have a finding, we have the feedback in our CI/CD pipeline. Okay, this fast test case found this and that area. We have the reproducing crashing input. So this is also a nice thing of fuzzing, that you directly get the crashing inputs. You don't have a false positive, or you don't have to go to cryptic compiler warnings or static code analysis warnings. There is evidence like, okay, for this input, it crashes. And on the other side, you also can take a look at the dashboard. How was the execution speed? Like, how well is performing your fuzzer? What code paths in your code is reached and what not. So this is also interesting that, for example, if some parts of your code are not covered by the fuzzer, because maybe your fuzz test case is not specific enough and you don't get along some magic values, or you don't it's too complicated for the fuzzer to get deep into some part of your program, then maybe you can rewrite the fuzzer and be more specific in some parts, or you can maybe also write a dedicated fuzzer for a dedicated subpart which it's not covered. So this feedback is also very important. So there's also nice that you have a dashboard and you can take a look at the coverage and your different campaigns you're running, and so to be up to date. So this is how we use CI Fuzz and CI Sense. So it's our infrastructure and our approach here. And so how long we have to fuzz? It's actually quite a long time. So here you see the average age and current average car age currently in Germany is like about 10 years. So this is data from 2023, and this is only of the current cars. And if we take the car lifetime until it's scrapped, in Germany this is like 15 years, and in other countries it's much longer. So in Poland it's like 35 years. So we have to maintain and test our software basically for 15 years. So there it's good that we can keep the corpus and the test cases for 15 years and execute them over and over again. And if we add new features, it's easy to detect regressions then, because like once we have on crashing input, we will have this input in our corpus, and then we can run it again. And often if you introduce a bug again, which you fixed some time before, you will easily then test it with fast test case to get all these regressions. And it's then detected, and you don't deploy, for example, this feature which will have, or this bug fix will have this regression. So it's good to detect. And maintenance is a very important topic, and we have to do testing for a long time. So in conclusion, it's very important to automate things. So everything you have to do manually, it's always error prone, or you might forget it, or yeah, my computer is not working and so on. That's not good. So the best thing to have tests which are automatable. So we want to fuzz in our CI/CD. We want to do it regularly, and we want to do it for 15 years. I hope I convinced you that memory safety is a real threat in the automotive space, and we need to tackle this thing. So in the long run, replace it with memory safe languages. And in the current situation, we need to intensively test these memory unsafe codes, especially where we pass untrusted input. And a good fuzzing tools and the infrastructure is a key here. So you need to have an infrastructure, you need to have a scalable infrastructure, and make it very easy for your developers to write fast test case, to execute them, and train them and onboard them that they are enabled to write fast tests themselves. So I think it's hard if you separate the testers from the projects, because it's sometimes very hard, for example, to just build the project, because the projects adapted their build system so much that for an external one, it's more challenging to learn their build system, that if the developers learn to write this fast test case together, and then later they can write their tests themselves, and they can just rely on you that you will support the infrastructure and deal with the findings and so on. And finally, if you fuzz automotive software, for example, if you're a security researcher, or if you are a customer and you find some vulnerabilities in our software, feel free to write an email to this email address, and we will handle then this issue and try to fix it. I think that's it from my parts. And
all right, thank you, Andreas, for that. We're going to open the floor up now to Q&A session. We've already had a couple of questions come in, so I'll begin reading those out now. How do you see or use Ethernet protocol security that is widely used in automotive software-defined vehicle architecture? Andreas? Andreas, you still with us?
So I see some questions. So should I go on and answer them?
Yeah, I'll read them out, and then if you could answer, that would be great. So we've had a question here. How do you see or use Ethernet protocol security that is widely used in automotive software?
Maybe I just go on. So the one question was like, ROS is a memory safe language in comparison to C and C++. Could you please provide other safe languages? So so Rust basically is the main safe language for the embedded space. But of course, for example, in infotainment, you use in the user application, you can use like Kotlin or Java, so they are memory safe. Swift is memory safe. There are currently some proposals to have C++ successor languages like Carbon, for example, is from Google. They want to have high interoperability between C++ and Carbon. So because Rust, it's hard to mix with C++, so it's better mixed with C. So there's Carbon. I think then Microsoft has like CPP front. Have more safe defaults than in C++. And I think also Adobe tries to have a successor language for C++. I think it's called now Hilo. Before it was called Val. But basically anything which is not C and C++ is memory safe. So also other languages like Python, and they are basically memory safe because they are interpreted. But for example, Python itself is written in C. So you could also trigger some memory safety bugs from the Python interpreter itself. Or some libraries written in Python, also written in C, that they are more performant. the next question was like, could you please share the reference book papers used in this presentation? Yeah, so all the books, papers, and so on, they should be are there mentioned as a link. And if you have the slides, you can click on them, and then you should get the references. Do you have any experience with static code analysis based on AI? Not at the moment. So of course we take a look. I read some paper, but yet I haven't used anything in production there. It's definitely interesting what the whole AI thing is offering. And yeah, so you could also use AI, for example, to write fast test case. But yeah, so if AI can detect dynamic problems, I don't know if this is how promising this is. So it's still questionable how good it will be. So at the moment, still fuzzing is the best tool to detect memory safety issues. So we will see if they will get better and how this. Okay, so Stephen said he will read the questions. Okay.
Yeah, sorry. So we had a couple come through a bit earlier that I just wanted to go over. So we've had someone ask, how do you see Ethernet protocols security that is widely used in automotive software-defined vehicle architecture? So I'm not sure if that came through. We had one saying, how do you use or see Ethernet protocol security that is widely used in automotive software-defined vehicle architecture? You still with us, Andreas? All right, guys, we may have...
Yes, so I can't hear anything, so everything is... I
think Andreas is having...
I can read the chat, but I don't hear.
I think he's having a bit of a problem with his microphone hearing his side. So I'll get Andreas to read out the questions and he can answer.
If it's okay, I would just continue reading because I can read the chat, so I can continue with the questions there. And so one question there was, how do you see Ethernet protocol security that is widely used in automotive software-defined vehicle architecture? Yeah, so I think there's definitely improvement to use Ethernet protocols. For example, compared to CAN, back then the CAN protocol has no security properties at all. So basically you have just a bus and everyone can read the bus and everything is a broadcast message, and you don't have integrity checks, you don't can check the authenticity and so on. So I think if we're using Ethernet protocols, there are some approaches to have also secure some IP, and yeah, so there definitely it's improved in the security sense. Also, if you take a look at, for example, the HTTP 3 and over QUIC, so there already it's encrypted and it's already based inside the protocol definition that security is there. Also, for example, MACsec, some technology where you can encrypt a MAC layer. There are definitely a lot of more security protocol or like security measures implemented already in the protocol, and not like in the past system where like security was the after product in the design. So I think there's definitely some improvement in the current software stack, but still we have to test our parsers and how we deal with the packages we receive over the network. Yeah, so one question, if we move away from memory safe language, do we still need fuzzing? Yeah, so as I mentioned, so we saw that there's this whole pie. So one part is memory safety, and like if we eliminate all the memory safety parts, we still have the other part, and probably also the attackers then will focus more on the other part, so on the non-memory safety issues. At the moment, it's just too easy or too daunting to use memory safety issues, because they can exploit a vulnerability in a, for them, nice way. And maybe if we have everything transferred, also I think it will take a very long time to have everything in a memory safe language. So there will still be a lot of things left, and also some parts you still have unsafe constructs, for example in Rust, memory mapped IO and things like this. You cannot do this in a safe manner, so you still have some unsafe blocks you need to fuzz, but then you can you can have a very focused way of testing to know where your unsafe parts are, and then you can fuzz these unsafe parts. Yeah, so then what could increase the adoption of developing writing fast test cases? So as I said before, if we have nice tooling, for example, if we have a way to auto-generate a first fast test case, and then the developer just has to add some properties here he wants to test or to make the quality a bit better, but where he can start with an initial fast test. Also maybe in Go, they have this in the language itself, so you don't need a special compiler, but fuzzing is a part of the language itself. So this also helps to make it very easy. And yeah, I also think Code Intelligence, they have very nice tools to make fuzzing easier for the developer. So, and there's still new things to come. So I think that's very promising to make it easier for the developers to write the fast test case themselves. And last question, what problems do you face when fuzzing automotive software? So as I showed in the beginning, like we sometimes have a very complex supply chain. So we sometimes get only binaries and from different vendors. And in the ideal case, they would already fuzz their software. So if everyone along the supply chain fuzz their software, it would be much securer. And also, for example, if they would deliver an instrumented binary, for example, you could also do some integration test where all the components are instrumented, and you can run different components in a fuzzer and detect also crashes in third-party libraries you get delivered in the integration test. Yeah, and sorry. Yeah, so curious about the role of AI, machine learning in software testing. What's the forecast for the next few years? I think there is a lot of work. I saw like for test case generation with large language models. So I think there is very promising. Then also there's some protocol fuzzers using large language models. Yeah, so I think there machine learning will help a lot to generate tests and to find where you can write a test. So you can use fuzzing to have these tests written in by an AI model. Of course, you need to do maybe some refinement. And on the other side, if you run like everything, if you generate your code itself by a machine learning model, so you probably also need to do more testing, because you just copied your code from some AI model and you don't know if it has any vulnerabilities or not. You need to assure the quality, so you can do this with excessive fuzz testing, so that okay, here I added something from a machine learning model. I need to thoroughly test it that it doesn't contain any vulnerabilities, or it didn't learn from bad code from GitHub, for example, and it didn't replicate bad practices. Okay, consider your next question. Consider your software extended fuzz tests over period time, and now you have the coverage report. How do you convince yourself or an external assessor that the fuzz tests cover your code sufficiently? Yeah, that's a good question. So also like when to stop your fuzzing. So sometimes maybe your fuzz test case like doesn't increase over time, and then maybe suddenly there would be an increase, but you already stopped. But I think you should at least have like a fuzz test case for each interface you have. So you should show that, okay, I considered this as an input and I have identified this function as a security relevant function because it uses, it has an interface to the outer world. It parses untrusted input. I can show, okay, this kind of coverage is reached. I can not, I go over the first condition. So there's a sufficient coverage. It goes deep enough. So I don't know if you can have like exactly numbers there to say, okay, we have something in Volkswagen, the group requirements, CARIAD for software. So they are specific coverage requirements for unit tests, which are 100%, I think. Sometimes it's very hard. So maybe you can say, okay, I want to achieve this kind of coverage report. And when you don't reach it, maybe you can say, okay, this is not reached because this input cannot be generated, or this is very hard. So maybe it's easier to argue why you can't reach the 80% or something. And yeah, and basically the best thing you can show is that, okay, here I do arithmetic on pointers or something, and this I have checked, or here these bound checks are very important because this sanitizes the input, and if it doesn't go through here, then okay, this is fine. Okay, I hope I answered the questions. I'm sorry for not hearing anything, so I hope you got something from me talking to the void, and yeah, I would give back to Stephen.
Yeah, I think we had some technical difficulties there from Andreas' side on hearing. I'm really sorry for that. Thank you very much for answering the questions that were supplied to us, and thank you for submitting your questions today. This video will be available on demand, so look out for the email link that gets sent to you. And on behalf of myself, Andreas, and Code Intelligence, I'd like to thank you for joining today. Enjoy the rest of your day.